Good morning everyone. I am Ranjit Kumar. Today we are going to discuss carbon fibers, production, properties and potential usages of them. A carbon fiber is a long thin strand of material which is about 5 micrometers to 10 micrometers in diameter and composed mostly of carbon atoms. The carbon atoms are bonded together in microscopic crystals that are more or less aligned parallel to the long axis of the fiber. The crystal alignment makes the fiber incredibly strong for its size. Several thousand carbon fibers are twisted together to form a yarn which may be used by itself or woven into fabrics. Okay, the yarn or fabric is combined with epoxy and wound or molded into shapes to form various composite materials. Carbon fiber reinforced composite materials are used to make aircraft and spacecraft parts, racing car bodies, golf club shafts, bicycle frames, fishing rods and automobile springs, sailboat masts and many other components where lightweight and high strength are needed. The fibers are extremely stiff, strong and light and are used in many processes to create excellent building materials. Carbon fiber material comes in a variety of raw building blocks including yarns, unidirectional waves, braids. What is a braid? A decorative and often silky cord or interwoven thread which is generally used in trimming, binding, decorating uniforms, edging for soft furnishings and several others which are in turn used to create composite parts. The properties of a carbon fiber part are close to that of steel and the weight is close to that of plastic. Thus, the strength to weight ratio which is also called as stiffness to weight ratio of a carbon fiber which is generally higher than either steel or plastic. Carbon fiber is extremely strong. It is typical in engineering to measure the benefit of a material in terms of strength to weight ratio and stiffness to weight ratio, particularly in structural design, where added weight may translate into increased life cycle costs or unsatisfactory performances. Carbon fibers. Okay, now let's see the brief history. Carbon fibers were developed in 1950s as a reinforcement of high temperature molded plastic components which are used in missiles. The first fibers were manufactured by heating strands of rayon, a synthetic textile fiber which is extracted from cellulose, until they are carbonized. This process proved to be inefficient as the resulting fibers contained only about 20% carbon and had low strength and stiffness properties. In the early 1960s, a process was developed using polyacrylonitrile as a raw material. This produced a carbon fiber that contained about 55% carbon and had much better properties. The polyacrylonitrile conversion process quickly became the primary method for producing carbon fibers. During the 1970s, experimental work to find alternative raw materials led to the introduction of carbon fibers made from a petroleum pitch derived from oil processing. These fibers contained about 85% carbon and had excellent flexural strength. Unfortunately, they had only limited compression strength and were not widely accepted. Today, carbon fibers are an important part of many products, and new applications are being developed every year. The United States, Japan, and Western Europe are the leading producers of carbon fibers. Okay, introduction of carbon fibers is all about what we have discussed till now. Okay, it's like 5 to 10 meters in micrometers in diameter, and it is mostly composed of carbon fibers and so on. So whatever points we have discussed till now, everything dealt about the introduction and a brief history of this particular carbon fibers. Okay, and it also has properties like low thermal expansion and various others, which make carbon fiber very popular in aerospace, civil engineering, military and motorsports, along with other competition sports. However, they are relatively expensive when compared with similar fibers such as glass fibers or plastic fibers. Okay, now let's move on to the classification and types of carbon fibers. They are classified by the tensile modulus of the fiber. Tensile modulus, it's a measure of how much pulling force a certain diameter fiber can exert without breaking. The English unit of measurement is pounds of force per square inch of cross-sectional area, or PSI. Carbon fibers, classified as low modulus, have a tensile modulus below 34.8 million PSI. And other classifications in ascending order of tensile modulus include standard modulus, intermediate modulus, high modulus, and ultra-high modulus. The ultra-high modulus carbon fibers have a tensile modulus of 72.5 to 145 million psis, or simply 500 million to 1 billion kilopascals. As a comparison, steel has a tensile modulus of about 200 million kilopascals. Thus, the strongest carbon fiber is about 5 times stronger than steel. Okay. The term graphite fiber refers to certain ultra-high modulus fibers made from petroleum pitch. These fibers have an internal structure that closely approximates the three-dimensional crystal alignment that is characteristic of a pure form of carbon known as graphite. Okay, now based on modulus strength and a final heat treatment temperature, carbon fibers can be classified into the following categories. First, based on carbon fiber properties, carbon fibers can be grouped into ultra high modulus type UHM, which is having modulus of more than 450 gigapascals. High modulus type HM, which is having the modulus between 200 to 350 gigapascals, and low modulus type, which is having between 200 to 350 gigapascals, and the low modulus and high tensile type having modulus less than 100 gigapascals and tensile strength more than 3 gigapascals. Okay, and super high tensile, which is more than. Okay, next we have is based on precursor type. It is classified into pan-based carbon fibers, pitch-based carbon fibers, mesophase pitch-based carbon fibers, isotropic pitch-based carbon fibers, rayon-based carbon fibers, and gas phase grown carbon fibers. Okay, now based on final heat treatment temperatures, carbon fibers are classified into type 1, which is high heat treatment carbon fibers, where final heat treatment temperature should be above 2000 degrees centigrade and can be associated with high modulus type fiber. The next is type 2, which is intermediate heat treatment carbon fibers, where the final heat treatment temperature should be somewhere around or above 1500 degrees centigrade and can be associated with the high strength type fiber. Right? And the next we have is type 3, which is low heat treatment carbon fibers, where final heat treatment temperatures not greater than 1000 degrees centigrades are used. These are low modulus and low strength materials. Okay, next, the manufacturing process. Raw materials are very important, right? The raw material which is used to make a carbon fiber is called as precursor. About 90% of the carbon fibers produced are made from polyacrylonitrile. The remaining 10% are made from rayon or petroleum pitches. All of these materials are organic polymers characterized by long strings of molecules bound together by carbon atoms. The exact composition of each precursor varies from company to another and is generally considered a trade secret. Okay, during the manufacturing process, a variety of gases and liquids are used. Some of these materials are designed to react with the fiber to achieve a specific effect. And other materials are designed not to react or to prevent certain reactions with the fiber. As with the precursors, the exact compositions of many of these process materials are considered as trade secrets. The process for making carbon fibers is part chemical and part mechanical. The precursor is drawn into long strands or fibers and then heated to a very high temperature without allowing it to come in contact with oxygen. Without oxygen, the fiber cannot burn. Instead, the high temperature causes the atoms in the fiber to vibrate violently until most of the non-carbon atoms are expelled out. This process is called as carbonization, and it leaves a fiber composed of long, tightly interlocked chains of carbon atoms with only a few non-carbon atoms remaining. Here is a typical sequence of operations used to form carbon fibers from polyacrylonitrile. The first is spinning. Next is, in this, acrylonitrile plastic powder is mixed with another plastic or methyl acrylate or methyl methacrylate and is reacted with a catalyst in a conventional suspension or solution polymerization process to form a polyacrylonitrile plastic. The plastic is then spun into the fibers having one of several different methods. In some methods, the plastic is mixed with certain chemicals and pumped through tiny jets into a chemical bath or quench chamber where the plastic coagulates and solidifies into fibers. This is similar to the process used to form polyacrylic textile fibers. In other methods, the plastic mixture is heated and pumped through tiny jets into a chamber where the solvents evaporate, leaving a solid fiber. The spinning step is important because the internal atomic structure of the fiber is formed during this process. The fibers are then washed and stretched to the desired fiber diameter. The stretching helps align the molecules within the fiber and provides the basis for the information of the tightly bonded carbon crystals after carbonization. And the next stage is stabilizing. Before the fibers are carbonized, they need to be chemically altered to convert their linear atomic bonding to a more thermally stable ladder bonding. This is accomplished by heating the fibers in air to about 390 to 590 degrees Fahrenheit for about 30 to 120 minutes. This causes the fibers to pick up oxygen molecules from the air and rearrange their atomic bonding pattern. The stabilizing chemical reactions are complex and involve several steps, some of which occur simultaneously. They also generate their own heat, which must be controlled to avoid overheating the fibers. Commercially, the stabilization process uses a variety of equipment and techniques. In some processes, the fibers are drawn through through a series of heated chambers. In others, the fibers pass over hot rollers and through beds of loose materials held in suspension by a flow of hot air. Some processes use heated air mixed with certain gases that chemically accelerate the stabilization. Next we have is carbonizing. Once the fibers are stabilized, they are heated to a temperature of about 1830 to 5500 degrees Fahrenheit for several minutes in a furnace filled with gas mixture that does not contain oxygen. The lack of oxygen prevents the fibers from burning in the very high temperatures. The gas pressure inside the furnace is kept higher than the outside air pressure, and the points where the fibers enter and exit the furnace are sealed to keep oxygen from entering. As the fibers are heated, they begin to lose their non-carbon atoms plus a few carbon atoms in the form of various gases, including water vapor, ammonia, carbon monoxide, carbon dioxide, hydrogen, nitrogen, and so on. As the non-carbon atoms are expelled, the remaining carbon atoms form tightly bonded carbon crystals that are aligned more or less parallel to the long axis of the fiber. In some processes, two furnaces operating at two different temperatures are used to better control the rate of heating during the carbonization. Next is treating the surface. After carbonizing, the fibers have a surface that does not bond well with the epoxies and other materials which are used in composite materials. To give the fibers better bonding properties, their surface is slightly oxidized. The addition of oxygen atoms onto the surface provides better chemical bonding properties and also etches and roughens the surface for better mechanical bonding properties. Oxidation can be achieved by immersing the fibers in various gases such as air, carbon dioxide, or ozone, and in various liquids such as sodium hypochlorite or nitric acid. The fibers can also be coated electrolytically by making the fibers the positive terminal in a bath filled with various electrically conductive materials. The surface treatment process must be carefully controlled to avoid forming of tiny surface defects such as pits which could cause fiber failure, right? And next, here in this list I couldn't include it, but it is sizing. After the surface treatment, the fibers are coated to protect them from damage during winding or waving. This process is called sizing. Okay, coating materials are chosen to be compatible with the adhesive which is used to form composite materials. Typical coating materials include epoxy, polyester, nylon, urethane, and others. The coated fibers are wound into cylinders called bobbins. These bobbins are loaded into a spinning machine and the fibers are twisted into yarns of various sizes. Right. Next we have few things to look over. The first is quality. The size of carbon fibers does not allow visual inspection as a quality control method. Instead, producing consistent precursors, fibers, and closely controlling the manufacturing process used to turn them into carbon fibers controls the quality. Process variables such as time, temperature, gas flow, and chemical composition are closely monitored during each stage of the production. The carbon fibers as well as the finished composite materials are also subjected to rigorous testing. Okay. The common fiber tests include density test, strength test, amount of sizing, and others. In 1990s, the Suppliers of Advanced Composite Materials Association established standards for carbon fiber testing methods, which are now used throughout the industry. Right. The next thing which we have to look into is health and safety concerns. There are three areas of concern in the production of handling of carbon fibers: dust inhalation, skin irritation, and the effect of fibers on electrical equipment. Right. During processing, all the pieces of carbon fibers can break off and can circulate in the air in the form of a fine dust. The industrial health studies have shown that unlike some asbestos fibers, carbon fibers are too large to be a health hazard when inhaled. They can be an irritant, however, and people working in the area should wear protective masks. The carbon fibers can also cause skin irritation, especially on the back of hands and wrists. Protective clothing or the use of barrier skin creams is recommended for people in an area where carbon fiber dust is present. The sizing materials used to coat the fibers often contain chemicals that can cause severe skin reactions, which also requires protection. In addition to being strong, carbon fibers are also good conductors of electricity. As a result, carbon fiber dust can cause arcing and shorts in electrical equipment. If electrical equipment cannot be relocated from the area where carbon dust is present, the equipment is sealed in a cabinet or other enclosures. Okay, now next we are going to see the properties of carbon fibers. Carbon fiber has high strength to weight ratio, which is also known as specific strength. Okay, the strength of material is the force per unit area at failure, which is divided by its density. Any material that is strong and light has a favorable strength to weight ratio. Materials such as aluminum, titanium, magnesium, carbon, and glass fiber, high strength steel alloys all have good strength to weight ratios. Carbon fiber is very rigid. Rigidity or stiffness of a material is generally measured by its Young's modulus, and it measures how much a material deflects under stress. Right? You might have already known. The carbon fiber reinforced plastic is over 4 times stiffer than the glass reinforced plastics. That means almost 20 times more than pine, 2.5 times greater than aluminium. Okay, carbon fiber is corrosion resistant and chemically stable. Although carbon fiber themselves do not deteriorate, epoxy is sensitive to sunlight and needs to be protected. The other matrices, whether the carbon fiber is embedded in wherever the carbon fiber is embedded in, might be also reactive. It is electrically conductive, right? And this feature can be useful and be also sometimes a nuisance. If board building has taken it into account, just as aluminium conductivity comes into play. Okay, the carbon fiber conductivity can facilitate galvanic corrosion in fittings. Careful installation can reduce the problem. Okay. Next, resistance is the resistance to fatigue in carbon fiber composites is good. However, when carbon fiber fails, it usually fails catastrophically. Okay, without much to announce its imminent break. Damage in tensile fatigue is seen as a reduction in stiffness with large numbers of stress cycles, unless the temperature is high. The tests have shown that failure is unlikely to be a problem when cyclic stresses coincide with the fiber orientation. Carbon fiber is superior to E-glass in fatigue and static strength as well as stiffness. Carbon fiber has good tensile strength and or ultimate strength is the maximum stress that a material can withstand while being stretched or pulled before necking or failing. Necking is when the sample cross section starts to significantly contract. If you take a strip of plastic bag, it will stretch and at one point will start getting narrow. This is called as necking, right? It is measured in force per unit area. The brittle materials such as carbon fiber does not always fail at the same stress level because of internal flaws. They fail at small strains, and this testing involves taking a sample with a fixed cross-section area and then pulling it, gradually increasing the force until the sample changes its shape and breaks. Fibers such as carbon fibers, being only 2 by 1/10,000th of an inch in diameter, are made into composites of appropriate shapes in order to test. Fire resistance, non-flammable. Okay, depending upon the manufacturing process and the precursor material, carbon fiber can be quite soft and can be made into more often integrated into protective clothing for firefighting. Okay, nickel coated fiber is an example of it because carbon fiber is also chemically very inert. It can be used where there is fire combined with corrosive agents. Carbon fiber fire blanket excuse typos. Okay, the thermal conductivity of carbon fiber. Thermal conductivity is the quantity of heat transmitted through a unit thickness in a direction normal to a surface of unit area because of a unit temperature gradient under steady conditions. In other words, it's a measure of how easily the heat flows through a material. Because there are many variations on the theme of carbon fiber, it is not possible to pinpoint exactly the thermal conductivity. Okay, special types of carbon fiber have been specifically designed for high or low thermal conductivities. There are also efforts to enhance this feature. Okay, now next, low coefficient of thermal expansion. This is a measure of how much a material expands and contracts when the temperature goes up or down. Units are in inch per inch degree Fahrenheit as in other tables. The units are also not so important as the comparison. In a high enough mass differences in coefficients of thermal expansion of various materials can slightly modify the rig tensions. Next, the low coefficient of thermal expansion makes carbon fiber suitable for applications where small movements can be critical. The telescopes and other optical machinery is one of such applications. Okay, next we have is non-poisonous, biologically inert X-ray permeable. These qualities make carbon fiber useful in medical applications, prosthesis use, implants and tendon repairs, X-ray accessories, surgical instruments, and are all in development. Okay, although not poisonous, the carbon fibers can be quite irritating, and long-term unprotected exposure needs to be limited. The matrix, either epoxy or polyester, can however be toxic, and proper care needs to be exercised. Okay, carbon fiber is relatively expensive. Although it offers exceptional advantages of strength, rigidity, and weight reduction, cost is a deterrent. Unless the weight advantage is exceptionally important, such as in aeronautic applications or racing, it often is not worth the extra cost. Right? The low maintenance requirement of carbon fiber is the further advantage. It is difficult to quantify cool and fashionable, but carbon fiber has an aura and reputation which makes consumers willing to pay more for the gadget of having it. You might need less of it compared to fiberglass, and this might be a saving. Okay, the last one, carbon fibers are brittle. The layers in the fibers are formed by strong covalent bonds. The sheet-like aggregations readily allow the propagation of cracks. When the fibers bend, they fail at very low strain. Okay, now applications, but I didn't put here applications, characteristics, and all those things of carbon fibers. Okay, physical strength, specific toughness, lightweight aerospace, road and marine transport systems, and all these comes under applications. Okay, and based on properties, based on the different criterias, we have different areas of applications which we will be seeing in the next class. Okay, thank you.